Hi everyone, so I'm Robert Cleeley.
And I'm Taspas Liss.
And we're back doing some more quantitative branding and marketing communications research. So up to this stage we've loaded some data into R, we've installed packages, we've called them or loaded them, we've created objects and done various functions on them, and where we've got to is we've conducted a factor analysis on a purchase intention factor. We've realised there was one item that was problematic, and we've tested that through a reliability measure as well as the factor analysis. We've created another model through the factor analysis which doesn't have that in. So we've now got two objects, one called model 1, one called model 2, and we can actually
compare them
statistically, not just
so
how we feel about them.
So that's the best solution. If you can compare your models statistically, you should always compare your models statistically. And R that we're using does that in a very straightforward manner, which is not the same for other statistical packages. Yeah,
so we'll show you how to do that, and we'll also show you how to save the output of some of these operations. Because once you know how to do it, it's the same for everything. So first, let's compare the two models. So Tassos and I have just been having a look at this. And we thought, I had a suspicion that you could just do an Anova test, an analysis of variance on the two models. And I had a suspicion that if we create an object and we use R's inbuilt function called Anova, which you don't have to install any additional packages or load anything, it's just there. And then you give it, the parameters are these two objects, model 1, model 2. You could do this if you'd got a regression model, as well as the factor analysis models, whatever. And now if we call that object An for Anova, I mean, again you could call this anything, I could call it Tassos if I wanted to. It spits out the results. So do you want to talk us through them?
So that's the amazing part. So in R you can actually use Anova directly to test for difference between models, and you see that without telling R to do anything, it actually tells us that this Anova test is testing for differences between the two models. And we have our two models, model 1 and model 2, and what we see from the results is that it gives us a lot of information. So it summarizes some of the results we've gotten from the factor analysis, so the degrees of freedom in the two models, the chi-square, which is the main metric for the two models, and then of course it calculates the differences between those two models and whether these differences are significant. But it does it in its own way. So let's walk through them. The delta means difference. So delta comes from the Greek letter delta, which in mathematics is used to signify difference between two things. So delta df is the difference of the degrees of freedom, which is in our case 3, which is a large difference when we are dealing with small numbers of items. We also get the calculated difference between chi-squares, which in this case is 1.292. And the next part is quite interesting. We get the probability that this difference in chi-square is actually larger than 0. And the null hypothesis here is that the delta square is equal to 0, and the alternative hypothesis is that the delta chi-square is larger than 0. That's why the probability is 0.7, so it's larger than 0.05. So we reject the null hypothesis, and we know that the difference in chi-squares is definitely larger than 0. Then R calculates essentially another chi-square, not the maximum likelihood chi-square as the factor analysis, but the actual empirical chi-square, the chi-square based on the data, the raw data themselves. Again, we see that the differences the two models have here are significant and larger than 0. And finally, we get the differences in the Bayesian information criterion. So we were discussing with Rob before, and we were investigating BIC and how to use BIC to actually check differences between models. So BIC is an index, as I was saying before, an index of information. And it is an index of information that is relevant to the amount of items and the information these items represent. Now, when we are looking like here between two alternative models, we are looking to capture, or we're looking to keep the model that has a lower BIC. The reason why that happens is that we want models that are what we call parsimonious or simple in that sense. So
or efficient.
Or efficient, which is another good word. So we want the most efficient model, the model that captures the most information with the least amount of items. This is a very big difference between them. There's no point in actually testing whether it's different than 0. And it shows that model 2 with just 4 variables is much, much better than model 1. So by this point, we are completely certain that we have a legitimate reason to use the second model, that is to kick out our original problematic variable. And we did that by looking at the factor loadings initially, by testing the factor through a reliability analysis, and by comparing the two models eventually through an Anova test.
Yeah, so what we thought would be useful is, one of the reasons Tassos and I were discussing this was the output in R here is kind of difficult to read.
Yeah,
it's sort of unclear which
yeah.
column is referring to which. So there's a couple of solutions to that. You can use a different piece of software to communicate with R. A very popular one is called R Studio. Or you could just save this output as something, and that's really useful to know how to do that, because obviously a lot of the results you're going to want to include in your final research papers or studies or dissertations. You're going to want to have the factor loadings and so on and so forth.
And the bitter truth is that you do not want to simply cut and paste the output. It would look really bad inside a paper, a dissertation, or a report or anything like that. So we definitely want our tables and our figures to be well designed as such.
Yeah, and also just in cutting and pasting, humans go wrong.
Yeah.
And you can press the wrong thing. And so it's good to know just how to save something. And a really simple way to do that in R is just to use the CSV function. So it's going to save it as a comma separated file, like an Excel spreadsheet. And earlier on we used read in the CSV function, which tells R to read a CSV file. Well, now we're going to use the write component of it. And to do that we need to tell it what we want to write. So here's our object, our Anova test, which we called Ann. And then we need to tell it where to save it.
Okay.
So what we can do is we can just give it the name that we want. And actually, Tassos should be nudging me now because we've already got one, which I should delete.
Yeah.
So what this is going to say is, using this function, CSV, or write.csv, on the parameter and the input object and save a new CSV file with this name test. And then if I go to the appropriate folder, here is the outputs of that test, and you'll see it's exactly the same as what we had in R. Our degrees of freedom is the same, all the columns are the same, and we can make it a bit nicer and more readable. We can format it in a nice way if we want to put it into our final papers and studies. So that's simply how to save something as a CSV file. Now, a question Tassos asked me earlier on is, well, how does R know where to save that file? And here we need to think a little bit about how computers work. So computers have folders or directories, and R, when you open R, is going to make, in fact when you install R, it asks you what do you want to have as your working directory, the folder on your computer that it's working in. And you can check what that is by typing get wd.
Get working directory.
Get working directory, and you don't need to pass this any parameters, so the brackets can be 0. And this is where my working directory is. Now if you want to change the working directory, so before we think about changing it, so what this is basically saying is, when we do write CSV, R automatically puts the working directory in front of this.
Right.
So we don't have to keep typing it. Because, as you know, particularly on Windows machines, your working directory might be like
very long.
Users, Tassos, document, then it gets really complicated and you can easily make a mistake.
Yeah.
But let's just say we've got a new project and we want to put it in a new working directory.
Yeah.
We need to know the working directory, which is a bit annoying, but it's not that difficult to figure out, hopefully. And then all you have to do is type set working directory and then the name of it. So there we have whatever it might be.
Okay.
Now, as this is my computer and I don't have this file,
Yeah.
it might not work. We'll see what happens. Yeah.
Yeah.
It's not going to give it to us because, well, actually, it might just be because of this. Yeah, it cannot change the working directory because the working directory
doesn't exist. Yeah. So that means, Rob, that we need to create a directory and give it a name before we actually execute the command in R.
Exactly. Yeah. So we could solve this error by either using a directory that does exist, or creating this directory.
Yeah. Okay.
And then we could do it all again.
Yeah.
And once we've set a different working directory, we could save the file to it again. Now, if you don't want to do that, and there might be some reason that you don't, you could type the full address here manually.
Yeah.
But what you'll find as you start working on bigger projects, you might want to save numerous outputs throughout this a session, and it gets kind of annoying to keep having to type these things out again and again. But that's the basic way that you could do that to save the results of the factor analysis that we ran earlier, if you wanted to. So you could say, let's go model 2 loadings.
Yeah, so we're now saving the factor loadings from model 2.
One trick here is if you don't put the .csv, Windows won't know what it is, and it can get a bit confused.
Okay.
Let's see if this works. So now if we go to the directory, there it is.
Go.
And here's our loadings.
Yeah. Okay.
So hopefully now then we've got to a point where you can take a data set. We've looked at the different types of items, thought about scales, we've ran factor analysis, we've ran reliability analysis, we've compared two different models or two different factor analyses. There's different methods which we could have employed, so we could have done a principal components analysis, and that is part of the psych package as well. So if we go all the way back up to one of our models, we could, instead of using FA, have done a PCA.
And we would need.
And we'll get some. We should get some slightly different results. So that's a pretty good basis, I think. In doing this, we've learned a bit about objects. We've learned how to load and save data. We've learned about functions. We've learned about parameters. So we've actually learned a lot of the skills that you would just need to do almost any statistical test.
On a lot of different skills.